Okay, folks, today we're going to talk about 8B, doubling time, and half-life. You are going to want to have a calculator near you. We're going to be using that a little bit for this one. So, definitions. The time required for each doubling in exponential growth is called doubling time, and the time required for halving in exponential decay is called halving time. All right, and so here is a formula. After a time lowercase t, an exponentially growing quantity with a doubling time of uppercase t, t double, increases in size by a factor of 2 to the power of the lowercase t over t double. The new value of the growing quantity is related to its initial value by this formula. So new value equals initial value times 2 to the t over t double. All right, so we're going to apply that formula. So compound interest produces an exponential growth because an interest-bearing account grows by the same percentage each year. Suppose your bank account has a doubling time of 13 years. By what factor does your balance increase in 50 years? So they're not asking for a new value, they're just asking by what factor it increases. So we only need part of that formula, which is this piece, the 2 to the t over tw. So it will increase by factor 2 to the lowercase t. In this case, that's 50. That's the amount of time we're talking about, over t double, which is 13. That's our doubling time. All right. So we'll go to the calculator. Oops. 2 to the 50 over 13. So it'll increase by a factor of about 14.38. All right. So this is an approximation rule to find the double time formula. So for a quantity growing exponentially at a rate of p% per time period, the doubling time is approximately 70 over p. And it's important to note that this approximation works best for small growth rates and breaks down for growth rates over 15%. So you shouldn't use this approximation when p is larger than 15. All right, world population doubled in the 40 years from 1960 to 2000. What was the average percentage growth rate during this period? Contrast this growth rate with the 2012 growth rate of 1.1% per year. So we can kind of use this formula to answer that question. So we know that t double is approximately 70 over p, where p is our percent growth rate. So with that in mind, I can isolate p. I'm going to multiply both sides by p. All right, so now I have p times t double is about equal to 70. And then I can divide both sides by t double. Right, so p is approximately 70 over t double. And for us, that's 70 over, the doubling time is stated to be 40 years. All right, and so What is that? 70 over 40. 1.75. So that just tells us that the average growth rate over those 40 years is about 1.75%. So let's contrast that to the 2012 growth rate of 1.1%. So we can conclude growth has slowed significantly. All right. So for exponential decay, we get a similar formula that relates the new value to the initial value. Key difference is that now the factor, the exponential factor, is 1/2 t over t half. All right, radioactive carbon-14 has a half-life of about 5,700 years. It collects in organisms only while they are alive. Once they're dead, it only decays. What fraction of the carbon-14 in an animal bone still remains 1,000 years after the animal had died? So again, we're only looking for the fraction that remains. We're not looking for a new value. So in this case, we only need to use this piece of our formula, the 1/2 t over t half. All right, so fraction that remains is half the time over the halving time. So that's half. We're talking about a time frame of 1,000 years over the halving time. What does it say the half-life is? 5,700 years. So we're going to get an approximation and do this in the calculator. I'll do 1/2, raise it to the power of 1,000 over 5,700. So 0.885. All right, so we're going to say about 88.5% of carbon-14 still remains. And that's a process called carbon dating. That's how they date how old something is, like a fossil that they find. All right. Suppose that 100 pounds of Pu-239 is deposited at a nuclear waste site. How much of it will be present in 1,000 years? So here we are actually going to use the full formula. New value equals initial value times half t over t half. So I'm just going to write an abbreviated version of that. So new value equals initial value times half t over capital T, which is our half-life time. All right, and we're trying to solve for the new value. The initial value was 100 pounds times half 100,000. And we need the half-life of this radioactive material, which I should have provided you with. So give me a second and I will look it up for us. Be right back. Okay, so Pu-239 is plutonium. So what they make nuclear weapons from. And it has a half-life of 24,000 years. So that's information you would need to be given. All right, but now we can finish filling out our formula. So 100,000 over 24,000. All right, so let's go to the calculator. We're going to do 1/2. No, I'm sorry, we're going to do 100 times 1/2 to the power of 100,000 went too far. Out of 24,000. No, that's 10,000. Sorry. And I do need one more zero here. Okay. All right, so there's about 5.6 pounds remaining. Okay, so the approximation for halving time is the same as for doubling time. T-half is approximately equal to 70 over P, where P is the percent decay for over a certain time period, and you only want to use this as long as P is below 15. So suppose that inflation causes the value of the Russian ruble to fall at a rate of 12% per year relative to the dollar. At this rate, approximately how long does it take for the ruble to lose half its value? So in this case, T-half is approximately equal to 70 over, in this case, 12. I'm just going to do this one in the phone calculator. And so that's 5.83 years. All right. So there are actually precise formulas. They involve using logarithms. And again, you can just use your calculator for this. So for an exponentially growing quantity with a fractional growth rate r, the doubling time is this. So the only thing I want to point out here, r is a fractional growth rate, meaning decimal. So P is a percent, which is why I actually use 12 for P. R is a rate, so R, if it were 12%, we would let R be 0.12. Okay? So that's all you have to be careful about. In your calculator, the logarithm button that's called a common log, so it will be base 10. So you can find that button down here. So this is log base 10. All right. And so then we have the formula for exponentially decaying quantities here. So let's check a quick example over using those formulas. So a population of rats is growing at a rate of 80% per month. Find the exact doubling time. For this growth rate and compare it to the doubling time found with the approximate doubling formula. All right, so we're going to use this formula for the exact doubling time. So in our case, R equals 0.8. So, all right, T double is log 2 over log 1 plus 0.8. All right, and so from that, we're going to get a decimal approximation. So let's jump over to the calculator. Log 2 over log 1.8. So the doubling time is about 1.18 years. Oh no, I'm sorry, this was given in months, so not years. The rat population will double in 1.18 months. Now, if we were to use the approximation formula where T double is approximately 70 over percent growth rate, that would be 70 over 80. Which is 0.875 months. So not good, not a good approximation, but remember we're only supposed to use this approximation when the growth rate is less than 15%. And this is a growth rate well above 15%, it's 80. So you're not going to get a very accurate result there. Anyway, that's it. Go ahead and do the problem set. Have a good one.